Hey there, deep divers. Have you ever paused to wonder how chemists painstakingly build those incredibly intricate molecules? You know, the ones that become life-saving drugs or groundbreaking new materials. It's far more than just assembling carbon atoms into chains. Sometimes it's about cleverly swapping out one piece for another, or maybe even temporarily hiding a sensitive part of the molecule, sort of like a disguise, to let other, more critical reactions take place. Today, we're embarking on a deep dive into the fascinating world of functional group interconversion by substitution. We're drawing our insights directly from the comprehensive pages of Advanced Organic Chemistry, Part B Reactions and Synthesis. Our mission? Well, it's to unpack the critical ways chemists manipulate these functional groups using substitution reactions. We'll be focusing on their practical applications in synthesis, defining all those essential technical terms plainly, and, maybe most importantly, highlighting the aha moments that reveal the true genius behind molecular design. Get ready to think like a molecular architect.
Yeah. Absolutely. And what's truly fascinating here is how these seemingly simple bond-swapping reactions, they really form the absolute backbone of complex multi-step synthesis.
Yeah.
We're not just talking about changing an atom here or there, you know. We're looking at incredibly precise controlled transformations.
Yeah.
These are indispensable for making the molecules we rely on every single day. We'll delve into conversions at both saturated carbons, which often involve those foundational mechanisms like SN2.
Right.
And then we'll pivot to transformations at carbonyl groups where an addition elimination pathway typically dominates. And then, crucially, we'll explore the ingenious methods chemists use to protect and deprotect these groups in multi-step syntheses, which is really all about strategic planning and foresight in the molecular world. It's quite clever stuff.
Okay, let's unpack this first part then. Our source material tells us alcohols are ubiquitous in organic chemistry. They're incredibly common building blocks. But paradoxically, on their own, they're actually quite poor alkylating agents. That sounds a bit counterintuitive, doesn't it? Why is that the case? And what do chemists do to make them more cooperative? What's the fundamental chemical challenge we're up against here?
Yeah, you've hit on the core problem right away.
Yeah.
The fundamental challenge is that the hydroxide ion, OH, is a very, very poor leaving group.
Okay.
Imagine trying to push a square peg into a round hole. It just doesn't want to go. In a substitution reaction, a leaving group needs to detach smoothly and take its electrons with it. Hydroxide, because it's a strong base and therefore a poor conjugate base, it just holds on too tightly.
Right.
Now, you can activate alcohols by O-protonation. That's adding a proton to the oxygen. It makes it positive and transforms it into water, which is a good leaving group. However, the strong acidic conditions required for this are often just too harsh for other sensitive parts of the molecule. The bits you might be trying to preserve in a complex synthesis. So in many cases, chemists need a more gentle approach. They have to install a different, better leaving group onto the alcohol.
So they modify the alcohol first.
Exactly. And this is where sulfonate esters come in. It's a really clever and widely used trick. Think of them as a kind of Trojan horse for the hydroxyl group.
Okay.
Instead of trying to kick out hydroxide directly, you convert the alcohol into a sulfonate ester. Common examples include p-toluene sulfonate, often called a tosylate.
All right, tosylate, I heard that.
Or methane sulfonate, a mesylate. Or, for when you need something really potent, trifluene sulfonate or triflate ester. The aha here is understanding that sometimes you can't just force a bad leaving group out directly. You have to transform it into something that is an excellent leaving group, like a tosylate ion, RSO3.
Which is much happier leaving.
Much happier leaving. It's much more willing to depart, opening up that carbon atom for nucleophilic attack. This transformation turns an unreactive alcohol into a really versatile electrophile.
So we're essentially taking a fundamental limitation of the alcohol and chemically engineering a solution to it. It enables a whole new set of reactions. How is that achieved practically in the lab? What's the actual process for making these sulfonate esters?
Well, the usual method involves reacting the alcohol with a sulfonyl chloride like p-toluene picoyl chloride or methensulfonyl chloride, typically in a solvent such as pyridine, often at temperatures between, say, 0 and 25 degrees Celsius.
Yeah, and the pyridine.
Pyridine serves a dual purpose here. It acts not only as a solvent, but also as a base. It neutralizes the hydrochloric acid that's formed during the reaction.
Which is important.
Crucial, yeah, to avoid unwanted side reactions with any acid-sensitive groups you might have elsewhere in the molecule. An alternative, though maybe less common method, is to convert the alcohol to its lithium salt first, and then react that with the sulfonyl chloride. And for creating those really, really good leaving groups, the triflates, you typically use trifluoromethensulfonic and hydride in halogenated solvents, again, in the presence of a base like pyridine. A key benefit highlighted in the literature, and this is important, is that this ester formation step usually doesn't disturb the original carbon-oxygen bond.
Okay, so the stereochemistry of the carbon stays put during this step.
Exactly. So issues like rearrangement or racinization, that's the loss of the original 3D orientation, are generally avoided during this particular transformation. However, it's important to remember that you still need to be careful with sensitive systems. For instance, allylic sulfonates, which have a double bond near the sulfonate group, they can still undergo reversible ionization if conditions allow. And tertiary alkyl sulfonates, they're significantly harder to prepare and are generally less stable. They often prefer to undergo elimination reactions to form alkenes rather than substitution under standard conditions.
Okay, so it's a powerful tool, but not universally applicable without thought.
Precisely. Its application always requires considering the alcohol's specific structure.
That makes a lot of sense. Now, halides are incredibly important for building carbon bonds, as we've discussed in previous deep dives. But getting them from alcohol seems to have its own distinct set of challenges, especially according to the material we're looking at today. What are the common methods for this conversion, and what are some of their significant pitfalls?
Absolutely. Well, the most straightforward but often harshest way is using hydrogen halides. We're talking about reagents like hot concentrated hydrobromic acid for bromides or hydrochloric acid with zinc chloride for chloride.
Like the classic methods.
Exactly. These reactions can proceed by the SN2 mechanism for primary alcohols, which ideally gives inversion of configuration, or by the SN1 mechanism for tertiary alcohols. The main limitation here is the strong acidic conditions. They often limit the use of these methods to very, very acid-stable molecules.
Right. Not good for complex stuff.
Not usually, no. Furthermore, rearrangements can be a significant problem, especially with tertiary alcohols. Those carbocation intermediates can readily shift to a more stable position, leading to messy mixtures of products. So these methods are generally suitable only for simple, unfunctionalized alcohols.
Okay, so what are the alternatives for more delicate molecules?
Moving beyond those harsh conditions, a more general approach, suitable for alcohols that aren't overly acid-sensitive or prone to rearrangement, involves using halides of nonmetallic elements, things like thionyl chloride, SOCl2, phosphorus trichloride, PCl3, or phosphorus tribromide, PBr3.
Okay.
Let's take thionyl chloride as an example. The alcohol first forms a chlorosulfite ester intermediate. Now, what's fascinating about this particular conversion is that the mechanism by which this chlorosulfite converts to the chloride can actually vary, and this influences the stereochemistry.
Oh, interesting. How so?
Well, in aprotic nucleophilic solvents like dioxane, solvent participation can lead to retention of configuration.
Retention, so it keeps its 3D shape.
Exactly. The original 3D arrangement is maintained. However, in the absence of such solvent participation, you might get internal delivery of chloride or just simple external SN2 attack. And that leads to a product with inversion of configuration where the 3D arrangement flips.
Wow. So the solvent choice dictates the stereochemical outcome.
It can, yes. The research also mentions a very effective 1.1 mixture of SOCl2 and benzotriazole for rapid conversion, even for carboxylic acids, likely involving some sort of nucleophilic catalysis by the benzotriazole. Now, when we consider phosphorus tribromide, the alcohol first reacts to form a trialkyl phosphide ester, often with successive displacements of bromide ions. If you run this reaction in the presence of an amine, it can potentially stop at this phosphide ester stage because the amine neutralizes the hydrogen bromide that's formed. However, if the HBr isn't neutralized, the phosphide ester gets protonated, and then each alkyl group is converted to the halide by nucleophilic substitution by bromide ion. The driving force for breaking that carbon-oxygen bond is the formation of a very strong phosphoryl double bond, PUO. That's a highly favorable process energetically.
Right, drives with the reaction forward.
Exactly. Now, backside attack is generally expected, leading to inversion of stereochemistry.
Like typical SN2.
Yes, but the sources highlight that racemization and rearrangement can and do occur as competing processes, especially with branching. For example, converting 2-butanol to 2-butyl bromide with PBr3 is accompanied by about 10-13% racemization and even a small amount of T-butyl bromide, which is a rearranged product.
So not perfectly clean.
Not always, no. It shows it's not always a perfectly clean, stereospecific process in all cases. The extent of rearrangement generally increases with increasing chain length and branching of the alcohol. So these methods, while powerful, have their nuances and potential side reactions. So to really address these limitations and achieve milder, more selective transformations, chemists develop methods involving phosphonium ion activation. The general idea is to activate a trivalent phosphorus reagent, like triphenylphosphine, with an electrophile, like a halogen. This forms a highly reactive intermediate, an alkoxyphosphonium ion.
Okay.
This intermediate is then very susceptible to nucleophilic attack by a halide, with that strong phosphoryl bond formation acting as the driving force for the substitution, ensuring a high-yielding reaction.
Alkoxyphosphonium ion, that sounds like a mouthful. How does this concept actually translate into a practical reaction in the lab? Can you walk us through a common example?
Let's simplify it. Think of it like this.
Yeah.
A common reagent is triphenylphosphine, PPH3.
Right.
This PPH3 first reacts with a halogen, let's say bromine, to form an adduct, PPH3Br2.
Okay.
This adduct then reacts with the alcohol. The alcohol displaces a bromide ion from the adduct, forming that key intermediate, the alkoxyphosphonium ion.
Gotcha.
Crucially, this intermediate is then attacked by a bromide ion. This attack typically happens from the backside.
SN2 again?
Exactly, resulting in the desired alkyl bromide and triphenylphosphine oxide as a byproduct. The key benefit here, the aha moment, is that because the initial step of forming the alkoxyphosphonium intermediate does not break the carbon-oxygen bond.
Right, that happens later.
Yes, and the subsequent step proceeds by backside displacement on carbon. It ensures clean inversion of stereochemistry for the overall process. This is incredibly valuable for controlling molecular architecture, especially with chiral alcohols. For example, this method is so powerful it can even convert notoriously difficult substrates like neopentyl alcohol to chlorides with high efficiency.
Wow, that's usually prone to rearrangement, isn't it?
Very prone, yes. But this method handles it well. And there are many variations on this theme. For instance, using carbon tetrachloride or hexachloroacetone with triphenylphosphine can generate chlorophosphonium ions in situ.
In situ, meaning right there in the pot.
Exactly, formed right there in the reaction mixture, which makes the process very convenient and avoids handling preformed, sometimes unstable, reagents. And then there's the incredibly powerful and versatile Mitsunobu reaction.
Yeah.
A true Swiss Army knife in organic synthesis.
Ah, yes, the Mitsunobu. Hear that one a lot.
You do. It elegantly combines triphenylphosphine with a reagent like diethyl azotocarboxylate, often just called DED,
Okay.
and a nucleophile, for example, methyl iodide. This system converts alcohols to iodides with clean inversion of stereochemistry. In the Mitsunobu reaction, DED activates the triphenylphosphine, allowing it to form that critical alkoxyphosphonium ion, which then undergoes nucleophilic attack by the iodide. This reaction is extremely mild and versatile, making it a recurring star throughout modern organic chemistry for various functional group interconversions.
Seems like a go-to reaction for many tricky situations.
It really is. And finally, just to round it off, for specific cases where even milder procedures are needed, maybe when allylic rearrangement is a concern,
Right.
chemists can first convert the alcohol to a sulfonate, like a tosylate. This tosylate is then displaced with a halide ion. This approach avoids rearrangement because the CO bond is broken in controlled SN2 fashion rather than potentially forming a carbocation. Another mild and effective route involves the heterocyclic 2-chloro-3-ethylbenzoxazolium cation.
Okay, another complex name.
It is, but it works well. This reagent works by having the alcohol add to its electrophilic heterocyclic ring, displacing chloride. The activated alkoxy group then undergoes nucleophilic substitution, forming a stable byproduct, 3-ethylbenzoxazolene, which helps drive the reaction to completion. For instance, it can convert a secondary alcohol to a chloride with inversion, confirming its stereospecificity.
It's quite remarkable how many distinct tools are in the chemist's toolbox for what seems like a single transformation, getting a halide from an alcohol. From those more straightforward but sometimes harsh acid-base conversions to the clever use of phosphorus reagents to that incredibly versatile Mitsunobu reaction, it really highlights the depth of the challenges chemists face and the precision required when choosing the right method for each molecular puzzle.
Absolutely. It's all about having the right tool for the right job and understanding the nuances of each one.
So we've covered how to activate our alcohols and get good leaving groups onto a carbon atom. Now let's talk about the next critical step, actually bringing in new functional groups using nucleophilic substitution, especially the SN2 mechanism. Our sources consistently emphasize its advantages, describing it as a synthetic chemist's dream. What makes SN2 so special and so desirable for precision synthesis?
Well, the SN2 mechanism is indeed a synthetic chemist's dream because it offers two critical advantages that directly impact the precision of building complex molecules. First, it's stereospecific, meaning that if you start with a chiral center, the reaction typically proceeds with a predictable inversion of configuration.
Right, the umbrella flip.
Exactly, giving you a known 3D outcome. This is invaluable when you're building complex structures with specific three-dimensional requirements, like in drug synthesis. Second, and perhaps even more valuable for avoiding messy side reactions, it avoids carbocation intermediates.
Ah, the
The
troublemakers.
definite troublemakers. This is incredibly important because carbocations are highly reactive and can easily rearrange, leading to messy mixtures of products and significantly lowering your yield. By avoiding them, SN2 reactions allow for the precise and controlled building of complex molecules. Now, to achieve that precise control and desired reaction rate, the choice of solvent is absolutely critical in SN2 reactions.
Yeah.
It's like picking the right environment to get the most out of your reactants. The solvent can significantly influence the nucleophiles' reactivity, almost supercharging it.
So, what are the superchargers of the solvent world for SN2 reactions, and what exactly makes them so effective at boosting reactivity?
We're talking about polar or product solvents, things like dimethylformamide, DMF, dimethylphosphide, DMSO, and hexamethylphosphorotriamide, HMPA. Although HMPA is used less now due to toxicity concerns.
Okay, DMF and DMSO are common. Why are they so good?
They are fantastic because they selectively solvate the correction of the positive ion. They essentially surround and stabilize it, but they leave the anion, which is our nucleophile, kind of naked and highly reactive.
Naked.
Yeah, less solvated, less shielded. In contrast, in product solvents like alcohols or water, the anions are heavily solvated by hydrogen bonding.
Right, they get surrounded by solvent molecules.
Exactly, which shields them and reduces their reactivity, almost like a protective bubble. But in polar or protic solvents, that bubble isn't really there for the anion, leaving it much less encumbered, thus significantly enhancing its nucleophilicity. For example, in DMF, the halides, iodide, bromide, chloride, they show comparable nucleophilicity, which is unlike in hydroxylic solvents where iodide is much more reactive than bromide, which is more reactive than chloride.
So it levels the playing field for halides.
It does. The real takeaway about polar or protic solvents isn't just what they are, but why they're revolutionary.
Yeah?
They effectively unmask the nucleophile, allowing reactions to happen dramatically faster and under much milder conditions than ever before. It's like taking the brakes off your molecular reactivity.
Okay, that's a powerful effect. Are there other tricks besides just changing the solvent?
Yes, absolutely. Beyond these traditional solvents, two other clever approaches leverage solvation effects to further boost reactivity: crown ethers and phase transfer catalysis.
Crown ethers, right? Those ring-like structures.
Exactly. They're a fascinating family of cyclic polyethers, like 18 crown 6. They have a specific cavity that's just the right size to encapsulate and complex the occasion, like potassium ions for 18 crown 6. By doing this, they can effectively solubilize salts, even in nonpolar solvents, which is usually very difficult.
Right.
The really important part is that with the cation caged inside the crown ether, the anion is left weakly solvated and therefore highly reactive as a nucleophile. This effectively stops tight ion pairing, allowing nucleophilicity to approach or even exceed what you see in the best of product polar solvents.
Wow. But you mentioned a safety concern.
Yes, it's important to note, as the research warns, that some crown ethers can be toxic, and they might transport toxic anions, such as cyanide, across the skin. That's a significant safety consideration in the lab.
Good point. And phase transfer catalysis.
Phase transfer catalysis, or PTC, is another brilliant strategy. It's particularly useful for two-phase systems where your reactants are in different immiscible solvents, for instance, an organic phase like dichloromethane and an aqueous phase containing your nucleophile salt.
Okay, so they can't normally mix and react.
Exactly. Without a catalyst, these systems show little reaction because the nucleophile stays in the water and the organic reactant stays in its layer. But when you add a phase transfer catalyst, typically a lipophilic quaternary ammonium or phosphonium salt with large hydrocarbon groups.
Lipophilic means fat-loving, right? So it likes the organic layer.
Precisely. It shuttles the anion from the aqueous phase to the organic phase. Once in the organic phase, the anion is weakly solvated and becomes a potent nucleophile, allowing reactions to proceed under much milder conditions than would otherwise be possible. A classic example that highlights its efficiency is converting 1-chlorooctane to octyl cyanide. You can get a 95% yield in just 2 hours at 105 degrees C using PTC. That's very efficient and practical.
That's impressive. So let's talk applications. Nitriles seem important.
Yes, nitriles are incredibly important building blocks in organic synthesis. Replacing a halide or sulfonate with a cyanide ion is a classical reaction that achieves something crucial. It extends the carbon chain by 1 atom.
Adding 1 carbon. That's useful.
Very useful. It's a direct gateway to carboxylic acid derivatives like acids, esters, or amides, after hydrolysis. While classical conditions involve heating a halide with a cyanide salt in aqueous alcohol, using those polariprotic solvents like DMSO or employing phase transfer or crown ether catalysis significantly speeds up these reactions, making them much more practical. For instance, primary alkyl chlorides can be converted to nitriles in an hour or less in DMSO at 120–140 degrees C. Interestingly, when using crown ether catalysis with solid potassium cyanide in acetonitrile, chlorides are actually more reactive than bromides.
Really? That's the opposite of normal SN2 leaving group ability.
It is. It's a reversal of the typical order seen in prokaryotic solvents and showcases the profound impact of these solvation effects on reactivity. It's also important to remember that secondary halides react slower due to competing elimination reactions.
The E2 pathway.
Right, and tertiary halides are generally not suitable for nitrile formation via SN2, as elimination becomes the dominant pathway. This highlights the selectivity and limitations of the SN2 reaction based on the substrate structure.
So we've discussed nitriles, which are fantastic for extending the carbon chain by one atom. What about introducing other vital oxygen-containing functional groups like ethers and esters?
Good question. Well, converting halides directly to alcohols isn't actually widely used in synthesis, mainly because alcohols are usually easier to obtain than their corresponding halides.
Makes sense.
However, the hydrolysis of benzyl halides to benzyl alcohols is a useful transformation because benzyl halides are often readily available. So it's a practical method for that specific type of alcohol. Now, ether formation, specifically the Williamson ether synthesis, that's incredibly important.
Williamson ether synthesis, okay.
This involves reacting an alkoxide, the conjugate base of an alcohol, with an alkyl halide or tosylate. A very common and practical application is converting phenols to methoxyaromatics using methyl iodide, methyl tosylate, or dimethyl sulfate as the alkylating agents. This reaction often proceeds efficiently with a weak base like potassium carbonate to deprotonate the phenol.
And for regular alcohols?
With alcohol alkoxides, which are considerably more basic than phenoxides, beta elimination can be more of a problem, so conditions must be carefully chosen. Fortunately, the most useful and commonly encountered ethers in synthesis are methyl and benzyl ethers.
Why them specifically?
Well, elimination is generally not a problem with methyl or benzyl groups, and their corresponding halides are especially reactive toward SN2 substitution. Phase transfer conditions can also be used effectively in more challenging cases to enhance reactivity, for example, making them amenable to less reactive substrates.
Okay. And esters via SN2?
For esters, there are two main SN2-related strategies. First, reacting carboxylic acids with diazo compounds, especially diazomethane or its safer alternative, trimethylsilidizomethane.
Diazomethane sounds reactive.
It is. It's an incredibly fast and clean reaction. The alkylating agent is actually the extremely reactive methyl-diazonium ion, which is generated by proton transfer from the carboxylic acid to diazomethane. The collapse of the resulting ion pair with loss of nitrogen gas is extremely rapid, making it a very efficient process, typically yielding the methyl ester and nitrogen gas.
But dangerous.
The main drawback for diazomethane itself is its toxicity and potential explosiveness, which is why safer alternatives like trimethylsildiazomethane are often preferred today.
Okay. What's the other strategy for esters?
Second, and particularly for larger scale work where safety is paramount, esters can be more safely and efficiently prepared by alkylation of carboxylate anions with alkyl halides or tosylates.
So the salt of the acid.
Exactly. Carboxylate anions are generally not super reactive nucleophiles, though. So optimal results come from using those polariprotic solvents or crowned ether catalysts to enhance their reactivity. Interestingly, the reactivity order for carboxylate salts follows the cation: sodium, potassium, rubidium, cesium.
Cesium is best.
Cesium carboxylates are especially useful in polariprotic solvents due to their high solubility and minimal ion pairing with the anion. This enhanced reactivity makes them excellent for preparing hindered esters, which can be tough to make by standard acid-catalyzed esterification, also known as Fischer esterification.
Right.
And there's a particularly clever application, often involving the versatile Mitsunobu reaction again.
Here it comes again.
It's everywhere. This application is the inversion of configuration at an oxygen-substituted center. It's a powerful method for precisely controlling molecular architecture. You activate a hydroxyl group, say, using Mitsunobu conditions with triphenylphosphine and DED, and then displace it with a carboxylate anion.
Okay.
The resulting ester now has the inverted stereochemistry at that carbon. Then subsequent hydrolysis of this ester yields the alcohol with the completely inverted stereochemistry. It's a precise way to flip the 3D orientation of an alcohol.
Wow, that's elegant.
It is. And this method also extends to preparing sulfonate esters with inversion, for instance, using zinc tosylate under Mitsunobu conditions.
Amines are a bit like that overeager friend who wants to react with everything at once. Our sources point out that direct alkylation often leads to multiple alkylations, forming secondary, tertiary, and even quaternary ammonium salts. This sounds like a recipe for a messy product mixture. How do chemists manage this overreactivity for precise control, especially if they only want to add one alkyl group?
You've perfectly captured the alkene's enthusiasm. Direct alkylation of primary amines is indeed problematic. The initial monoalkylated product is still a nucleophile, and often a stronger one than the starting primary amine.
So it reacts again, even faster.
Exactly. So it can react sequentially to form secondary, tertiary, and even quaternary ammonium salts if an excess of alkylating agent is present. Even with a limited amount of alkylating agent, the equilibria between protonated product and the neutral starting amine are sufficiently fast that you often get a mixture of products anyway.
So what's the best way to get just monoalkylation?
If you want precise monoalkylation of a primary amine, the most elegant solution chemists have come up with is usually reductive amination. That's a reaction discussed in a later chapter of our source, but it forms the amine in a single controlled step.
Okay, so that's often preferred.
Usually, yes. However, if complete alkylation to the quaternary ammonium salt is actually what you want, then using excess alkylating agent and a base to neutralize the liberated acid usually works well. For more precise control, especially of primary amines, the Gabriel synthesis is a classic and elegant method.
Gabriel synthesis.
It uses the phthalimide anion. This anion is readily alkylated by alkylamines or tosylites because the NH group in phthalimide is considerably more acidic than in simple amines. This forms an alkylphthalimide. The primary amine is then liberated from this N-alkylphthalimide using hydrazine.
Hydrazine, right?
Which involves a sequence of additional amination and intramolecular acyl transfer steps. There are now also milder deprotection methods, like using sodium hydroxide, that accelerate this process.
That's a way to protect the amine, alkylate it once, then release it.
Precisely. Now, secondary amides can be N-alkylated too, but you usually need to deprotonate them first with a strong base like sodium hydride, then react with an alkyl halide. And neutral tertiary and secondary amides can even undergo O-alkylation by very reactive alkylating agents like triethylhexonium tetrafluoroborate, forming iminoculars after neutralization.
Okay.
Sulfonamide anions are also good nitrogen nucleophiles. Yeah. And the Mitsunobu reaction, yes, again, can introduce sulfonometal groups at benzylic positions with a high level of inversion of stereochemistry.
It's just so useful.
It really is. The Mitsunobu reaction also facilitates alkylation of 2-pyridones, which is relevant in synthesizing some anti-tumor agents, and can even be used for cyclization to make propylene analogs. It's also effective for glycosylation of weak nitrogen nucleophiles like indoles, used in other anti-tumor compound syntheses.
Clearly science.
These are incredibly useful intermediates in synthesis.
Why are they so useful?
Because they can be easily reduced to primary amines, and they participate in important cycloaddition reactions, like the famous click reaction.
Click chemistry. Right.
Exactly. Azides are typically introduced into aliphatic compounds by nucleophilic substitution, usually by heating halides with sodium azide in a polar protic solvent like DMSO or DMF, or using phase transfer conditions. Interestingly, azides can also be prepared directly from alcohols using reagents like 2-fluoro-1-methylpyridinium iodide followed by lithium azide, or by using diphenylphosphoryl azide in the presence of triphenylphosphine and dead
Mitsunobu
under Mitsunobu conditions. Both these methods again proceed with inversion of stereochemistry, highlighting the SN2 nature. Strong organic bases like DBU can also facilitate acetylide formation from alcohols with phosphoroazidates via O-phosphorylation followed by SN2 displacement.
So many ways to get an azide in there.
Yes, it's a very valuable functional group. Moving on quickly to sulfur and phosphorus nucleophiles. While maybe less common in everyday synthesis than oxygen or nitrogen nucleophiles, they're equally powerful and important. Thiolate anions are strong nucleophiles and alkylate readily, giving thioethers in high yields. Even neutral sulfur compounds like sulfides and thioamides readily form salts with methyl iodide, for example. Even sulfoxides, where the oxygen reduces nucleophilicity, can be alkylated by methyl iodide, forming sulfoxonium salts which have their own significant synthetic applications.
Okay. And phosphorus.
Phosphorus compounds, both neutral and anionic, are also excellent nucleophiles toward alkyl halides. We encountered examples of these reactions in a previous deep dive, specifically with the preparation of Wittig reagents. the phosphoranes and phosphonates, which are crucial for forming carbon double bonds.
Right, the Wittig reaction.
Sure. A notable example is the Michaelis-Arbuzov reaction. This involves phosphide esters reacting with alkyl halides. It proceeds through an unstable trialkoxyphosphonium intermediate. The second stage of this reaction is another prime example of the great tendency of alkoxyphosphonium ions to react with nucleophiles to break the carbon-oxygen bond. This results in the highly favorable formation of a phosphoryl PO double bond, which provides a strong driving force for the reaction.
That PO bond formation seems to be a recurring theme.
It is. It's thermodynamically very favorable and drives many phosphorus-based reactions. So to summarize the SN2 magic and the general rules of the game for planning synthetic steps, the research emphasizes these key reactivity principles. First, for the alkylating group reactivity, the order is generally benzyl allyl primary secondary.
And tertiary is bad for SN2.
Exactly. Tertiary halides and sulfonates usually lead to elimination instead. Second, for leaving group reactivity, the order is sulfonate, like tosylate or mesylate, iodide, bromide, chloride. Sulfonates and iodides are excellent leaving groups because they're weak bases. Third, and critically important for molecular design, steric hindrance decreases the rate of nucleophilic substitution. More bulky groups near the reaction center will slow down or prevent SN2 from occurring.
This means planning synthetic steps involving SN2 truly requires careful consideration of steric issues and the overall molecular environment. Looking at the various examples in the literature, we see all these principles come to life. For instance, you see the introduction of azazide at secondary carbons with inversion of configuration, which perfectly underscores the stereospecificity we just discussed. Or you can observe how chemists control the alkylation of the manganese to avoid those pesky multiple alkylations, perhaps by using excess amine or by strategically protecting one nitrogen. This really illustrates the practical application and ingenuity involved in using these principles to achieve precise outcomes. It's a masterclass in molecular strategy.
It really is. You have to think several steps ahead.
So far, we've focused on making new bonds and interconverting functional groups. But sometimes, especially in complex synthesis, you need to go in reverse. You need to break a carbon-oxygen bond, say in an ether or an ester. According to our sources, these can be quite stubborn. What's the fundamental challenge here, and how do chemists tackle it without destroying the rest of their carefully constructed molecule?
Yeah, you're right. They can be stubborn. The challenge is precisely that alkoxide and carboxylate groups are inherently very poor leaving groups.
Right, just like hydroxide was for alcohols.
Exactly the same principle. This means that unlike an SN2 formation where you create a good leaving group, these cleavage reactions typically require some assistance to effectively pull the oxygen away from the carbon. This assistance usually comes from a prothic acid, which protonates the oxygen, or a Lewis acid, which coordinates to the oxygen.
Making it want to leave more.
Essentially, yes. Making it more electrophilic and thus a better leaving group, or making the CO bond weaker. The classical methods for ether cleavage, like using hot concentrated hydrogen halides, are often just too harsh for complex, multifunctional molecules because they can lead to unwanted side reactions or degradation. The aha is that you often need a highly specific reactive species to induce these breakages gently. So milder, more selective reagents are absolutely essential for modern synthesis.
Okay, so what are these gentler giants?
Fortunately, chemists have indeed developed much milder yet powerful reagents for ether cleavage. One of these is boron tribromide.
BBr3.
This is a very powerful reagent, particularly effective for cleaving methyl ethers, especially aryl methyl ethers. The mechanism generally involves BBr3 forming an adduct with the ether oxygen, making that oxygen more prone to leaving. This adduct then undergoes nucleophilic attack by bromide. The cleavage step itself can occur by either an SN2 or an SN1 process, depending on the structure of the alkyl group being cleaved. Good yields are generally observed. The research mentions that a combination of BBr3 with dimethyl sulfide has been found to be particularly effective for cleaving aryl methyl ethers. Related to this is dimethyl boron bromide, B2BBr, another boron-based reagent that functions on similar principles for ether cleavage, offering another option.
Okay, what else is in the toolbox?
Then there's trimethylsilly iodide, TMSI. This is a true workhorse in organic synthesis for cleavages.
TMSI, right. Sounds silicon-based.
It is. This reagent can cleave metal ethers in a matter of a few hours at room temperature, which is quite mild. Benzyl and T-butyl systems react even faster, while secondary systems require longer reaction times. The reaction presumably proceeds via an initially formed silyl oxonium ion, where the silicon coordinates to the ether oxygen, making it more electrophilic and weakening the CO bond. Then iodide, acting as the nucleophile, attacks the carbon, leading to cleavage.
And the direction depends on the group.
Yes, the direction of cleavage in unsymmetrical ethers is dictated by the relative ease of OR bond breaking. It's usually an SN2 process for methyl or benzyl groups, and an SN1 process for T-butyl groups, leveraging the stability of the T-butyl cation.
Clever.
Because TMSI can be relatively expensive, practical ingenuity has led to methods for generating it in situ right in the reaction mixture.
Make it as you need it.
Exactly. From readily available precursors like trimethylsilyl chloride and sodium iodide, or from phenyltrimethylsilane and iodine. This makes the method much more practical for larger-scale synthesis. Diodosilane, ACH2I2, is also noted as being particularly effective for secondary alkyl ethers.
Okay. Any others?
Finally, boron trifluoride, BF3, in the presence of thiols, is another effective combination. This system works on the basis of nucleophilic attack by the thiol on an oxonium ion that's generated from the ether in BF3. The thiol acts as a soft nucleophile, attacking the carbon adjacent to the activated oxygen, leading to cleavage. This offers another mild selective pathway.
And TMSI works on esters, too.
It does. TMSI is not just for ethers, it also rapidly cleaves esters. In this case, the iodide attacks the ocylated ester, forming trimethylsilyl esters as initial products. These silly esters are then easily hydrolyzed to the desired carboxylic acids upon aqueous workup.
Very convenient.
It's particularly effective for benzyl, methyl, and T-butyl esters, which highlights its broad utility. For T-butyl esters, the initial silylation is followed by rapid ionization to the T-butyl cation, facilitating the cleavage, similar to its action on T-butyl ethers. Another powerful approach for ester cleavage involves acetic anhydride with Lewis acids, like FPeCl3 or MgBr2. The mechanism here is believed to involve highly reactive acylium ions, which are generated from the anhydride and the Lewis acid. These acylium ions are very electrophilic and readily attack the ester, leading to its cleavage and forming a new anhydride.
The examples from research really showcase the practical challenges and ingenious solutions in these cleavage reactions. For instance, you see boron tribromide cleverly used to deprotect a methyl ether, which then spontaneously lactonizes because the newly revealed hydroxyl group is perfectly positioned to attack an existing ester, forming a ring.
That's neat.
It is a nice cascade reaction. Another example from the literature highlights how challenging some of these cleavages can be. A complex benzylic ether with multiple activating substituents required careful conditions, specifically the presence of excess sodium acetate. Why the acetate?
To prevent side reactions and achieve the desired selective cleavage of a primary benzyl bond over a secondary one. It likely acts as a buffer or traps reactive intermediates.
Wow. This really underscores the precision and strategic thinking needed when dealing with sensitive and complex molecules, and how the right additives can fine-tune the reactivity to get exactly the bond breakage you want.
Exactly. Sometimes it's the small details that make all the difference.
So let's move on. Carboxylic acids and their derivatives, think acylhalides and hydrides, esters, amides. These are absolutely fundamental building blocks in organic chemistry. But transforming them from one form to another, especially when you have other sensitive functional groups in the molecule, can be a delicate dance. Why are these interconversions so important in synthesis, and what makes them particularly tricky?
Well, these interconversions are crucial because different carboxylic acid derivatives have wildly different reactivities. This allows chemists to perform specific reactions on them and then transform them into a lesser, more reactive form as needed. It's almost like changing gears in a car.
Okay, so you use the right gear for the right reaction.
Precisely. For instance, acyl chlorides are highly reactive for acylation reactions, readily forming esters or amides, while amides themselves are generally very stable and pretty unreactive. The challenge, and where the ingenuity comes in, is often achieving these transformations under mild, selective conditions. You want to avoid harsh reagents that might degrade other parts of a complex molecule. This requires a deep understanding of their individual reactivities and the specific mechanisms involved. The aha here is recognizing that you often need to activate the carboxylic acid for it to participate in a desired reaction.
Activate it. Make it more reactive.
Exactly. Let's start with the acylation of alcohols to form esters. The traditional way to make esters or amides from carboxylic acids is by first converting the carboxylic acid to an acyl chloride. For molecules that don't have acid-sensitive functional groups, you can use strong reagents like cyanyl chloride, SOCl2, or phosphorus pentachloride, PCl5.
The classics again.
Yes. However, when milder conditions are necessary, the research points to oxalyl chloride. If you react the carboxylic acid, or even better, its sodium salt, with oxalyl chloride, it provides the acyl chloride under gentler conditions. When a salt is used, the reaction solution remains essentially neutral, which is highly beneficial for sensitive substrates.
Why oxalyl chloride specifically?
Well, a fascinating detail about oxalyl chloride is its mechanism. It involves the formation of a mixed anhydride chloride of oxalic acid. This intermediate then efficiently decomposes, generating both carbon dioxide, CO2, and carbon monoxide, CO gas.
Gas evolution drives it.
Exactly. These are very stable byproducts, which provides a strong driving force for the reaction. What's more, the research highlights that treating carboxylic acids with just half an equivalent of oxalyl chloride can even generate anhydrides directly from carboxylic acids, a very efficient approach.
Interesting. Any other ways to make acyl halides gently?
Yes, another powerful approach uses triphenylphosphine with a halogen source. For example, triphenylphosphine and carbon tetrachloride convert carboxylic acids to the corresponding acyl chloride. Similarly, carboxylic acids react with the triphenylphosphine bromine adduct to give acyl bromides. Even triphenylphosphine with N-bromocyclanamide can generate acyl bromide in situ.
So similar phosphonium chemistry again.
Exactly the same principle. All these reactions proceed via acyloxyphosphonium ions, mechanistically analogous to the alcohol to halide conversions we discussed earlier. The strong driving force, again, is the formation of that PO bond in triphenylphosphine oxide.
Okay. Now, beyond just creating the acylating agent, I've heard about catalysts that can dramatically boost the reaction rate and allow for much milder conditions. What are the key players here that enable these precision acylations, especially for challenging molecules?
Absolutely. Catalysis is vital for achieving milder conditions and improved selectivity. Pyridine is a common catalyst. It works by forming an acylpyridinium ion, which is a more reactive intermediate than the acyl chloride itself, and then this ion reacts more rapidly with the alcohol. Pyridine is a better nucleophile than the neutral alcohol, making this an efficient catalytic cycle.
Okay, pyridine helps, but isn't there something even better?
Yes, the real superstar, widely celebrated in the literature, is 4-dimethylamidopyridine.
DMAP, right.
Adding just 520 mol% of diabyl can increase acylation rates by up to 4 orders of magnitude.
Wow, that's a huge difference. Why is it so good?
It achieves this because the dimethylamino group acts as an electron donor. This makes the pyridine nitrogen both more nucleophilic and more basic, thereby accelerating the initial activation of the acylating agent and its subsequent transfer to the alcohol. This phenomenal catalytic effect allows for successful acylation of even tertiary and highly hindered alcohols, which are notoriously difficult to esterify. Even more reactive systems combine an acid anhydride with magnesium bromide and a hindered tertiary amine, providing an exceptionally potent acylation system useful for extremely hindered and sensitive alcohols.
Amazing catalytic power. What about Lewis acids?
Lewis acid catalysis is another major category. Scandium triflate, COTF3, is a mild and incredibly effective catalyst for acylation, generating reactive acyl trislates. Mechanistic investigations indicate that triflic acid, generated in situ, is involved, and 2 catalytic cycles can operate. One involves only triflic acid, while another involves both the scandium salt and triflic acid. This approach can even acylate hindered tertiary alcohols, as beautifully demonstrated in the synthesis of anti-cancer agent camptothecin analogs. Other metal triflates, like those involving ytterbium or lutetium and bismuth-3 triflate, show similar powerful catalytic effects, even with less reactive anhydrides like benzoic and pivalic. Trimethylsulfide triflate is also an incredibly powerful catalyst for acylation by anhydrates, even allowing tertiary alcohols to react rapidly at 0 degrees C. The aha. Here is how specific metal ions, acting as Lewis acids, can dramatically lower the energy barrier for these transformations, making previously impossible reactions practical.
It's like they give the reaction a helpful push.
A very specific and effective push, yes. Beyond these, there are other very selective acylating agents. Imidazolides, which are N-acyl derivatives of imidazole, are a great example. They can be isolated and prepared directly from carboxylic acids using carbonyl dimidazole.
Why are they reactive?
Their reactivity stems from 2 factors. First, the relative weakness of the amide bond, because the nitrogen lone pair is part of the aromatic imidazole ring, so there's less NCO delocalization.
Okay.
And second, enhanced leaving groupability upon protonation of the other imidazole nitrogen. They are excellent for acylation of acid-sensitive materials, reacting with alcohols on heating and with amines at room temperature.
Okay. What about DCCI? That comes up in peptide synthesis a lot.
Dicyclohexylcarbodamide, DCCI, is indeed widely used, particularly famous in polypeptide synthesis. It activates the carboxylic acid by forming an O-cell isorea intermediate. This is a highly reactive species. The azo group becomes very reactive because the nitrogen is susceptible to protonation, and cleavage of the acyl-oxygen bond converts the carbon-nitrogen double bond of the isorea to a more stable urea-carbonyl group, dicyclohexylurea DCU, which precipitates out, providing a significant driving force.
Right, that insoluble urea byproduct.
Exactly. Combining DCCI with DMP offers a very useful in situ activation for reacting carboxylic acids with alcohols at room temperature, providing mild and effective esterification. Additionally, 2-chloropyridinium and 3-chlorosoxazolium cations also activate carboxyl groups by an additional elimination mechanism. In these cases, the halide is displaced from the heterocycle by the carboxylate. Nucleophilic attack on the activated carbonyl group then results in the elimination of the heterocyclic ring. The positive charge on the heterocycle accelerates both steps.
Clever activation strategy.
And finally, thiol esters, especially those of pyridine 2-thiol, are considerably more reactive acylating reagents than alcohol esters. This enhanced reactivity is due to the extra driving force from forming the stable pyridine 2-thione tautomer upon displacement.
Ah, tautomerization helps pull it along.
Exactly. Even more, cupric salts can further accelerate reactions, especially with hindered esters, demonstrating fascinating coordination chemistry at play. Pyridine 2-thiol esters can be prepared directly from the carboxylic acid using 2-2-pyridyl disulfide and triphenylphosphine, or from the acid N2-pyridyl thiochloroformate.
Creating large ring structures, like the ones found in many antibiotics, sounds incredibly challenging due to the need to favor intramolecular cyclization over intermolecular polymerization. How do these acylation strategies help with something as specific and difficult as macrolactinization? This seems like a true test of synthetic elegance.
It is a huge challenge, precisely because you need to favor that intermolecular cyclization over intermolecular polymerization, which would just lead to long polymer chains, consuming your precious starting material.
Right, you want the molecule to bite its own tail, not link up with others.
Exactly. The 2-pyridyl and 2-imidazolial disulfides used with triphenylphosphine are specially designed for this. It's suggested that their mechanism involves the heterocyclic nitrogen acting as a base, deprotonating the alcohol. This proton transfer is thought to provide a cyclic transition state where hydrogen bonding can enhance the reactivity of the carbonyl group, thus promoting the desired intramolecular cyclization. Research shows high yields for complex macrolactones using this very method, demonstrating its effectiveness for these challenging syntheses.
So the reagent helps hold the ends together.
That seems to be the idea. Another popular method for macrolactinization is the Yamaguchi method. This uses 2.4-6-trichlorobenzoyl chloride, triethylamine, and DMA.
Yamaguchi method, okay.
This reaction is thought to involve the formation of a mixed anhydride with the aroyl chloride, which then forms a highly reactive acylpyridinium ion upon reaction with DMA, specifically promoting cyclization. DCCI and DMA are also effective for macrolactinization, but crucially, almost all macrolactinizations must be done in very dilute solutions.
High dilution conditions. Why?
To maximize the probability of the intramolecular reaction occurring over competing intermolecular reactions, which would lead to dimers or higher oligomers. If the ends of the molecule can't easily find each other because they are far apart in dilute solution, they're more likely to react with themselves than with another molecule. The aha here is that dilution is a powerful yet simple strategic tool to control reaction outcomes, especially in ring-forming reactions.
It's amazing to see how tailored these methods are, from simple esterifications to the extreme complexity of macrocyclizations. It's a powerful visual of how chemists choose precisely the right tool for the job.
Absolutely. And we can't talk about esters without mentioning the classic Fischer esterification.
Ah, the undergrad lab classic.
Indeed. It's the acid-catalyzed reaction of carboxylic acids with alcohols. It's conceptually simple, but it's an equilibrium process. So to drive it to completion and get good yields, you either use a large excess of an inexpensive alcohol, effectively pushing the equilibrium to the product side.
Le Chatelier's principle.
Exactly. Or you irreversibly remove the water that is formed, often by azeotropic distillation, boiling off water as a mixture with another solvent like toluene. It's a simple but highly effective foundational method for ester synthesis, widely used in industry and academia.
Good old Fischer. Now, amides are another critical functional group found everywhere from proteins to pharmaceuticals. How do we make them, especially when trying to avoid side reactions or dealing with sensitive starting materials?
Well, the most common way to prepare amides is by reacting ammonia, or a primary or secondary amine, with a reactive acylating agent. such as an acid anhydride or an acyl halide, which we discussed earlier. Acid anhydrides usually give rapid acylation of most amines and are convenient if available. But remember, only one of the two acyl groups is converted to an amide, the other becomes a carboxylate.
Right.
When acyl halides are used, some provision for neutralizing the resulting hydrogen halide is necessary, as it will react with the amine to form an ammonium salt, consuming your amine reactant.
So you need a base.
Yes. The Schotten-Baumann conditions, which involve shaking an amani with excess anhydride or acyl chloride in an alkaline aqueous solution, provide a very satisfactory method for the preparation of simple amides, as the base neutralizes the acid byproduct. A great deal of work is focused on the in situ activation of carboxylic acids for reaction with amines, especially for polypeptide synthesis.
Right, making proteins.
Exactly. DCCI is a primary coupling agent here. It activates the carboxylic acid to react directly with the amine. Also, activated esters like p-nitrophenyl, 2,4-5-trichlorophenol, or anhydroxyacetynamide esters are widely used. These can be isolated and purified, and then they react rapidly with free amino groups to form amides. They're even used for the chemical modification of biological molecules, like attaching fluorescent labels to antibodies or photo labels to peptides.
Useful for biochemists, too.
Very much so. 1-hydroxybenzotresol, HOBT, in conjunction with DCCI is another powerful combination, often used for coupling one amino acid with another, with high efficiency and minimizing racemization. Mixed phosphoric acid derivatives are also employed. Diphenyl phosphorylazide, for instance, is an effective reagent for converting amines to amides. The proposed mechanism involves forming an acylazide intermediate, which is highly reactive. Another useful reagent for amide formation is BOPCl, bis-2-oxo-3-oxazolidinyl phosphinochloride, which also proceeds via a mixed carboxylic phosphoric anhydride, enabling efficient amide bond formation, particularly in peptide synthesis.
Lots of specialized reagents for peptide bonds.
It's a critical area. Now, a really interesting mild method for converting esters directly to amides uses aluminum amides. These can be prepared from trimethylaluminum and the desired amine. These reagents convert esters directly to amides at room temperature.
How does that work?
The driving force for this reaction is the favorable formation of strong aluminum-oxygen bonds relative to aluminum-nitrogen bonds. It effectively pulls the oxygen away from the ester and substitutes it with nitrogen. Similar reactivity is seen with trialkylmanotin, sutentinamides, and titaniumamides. These reagents can even catalyze exchange reactions between amines and ines under moderate conditions, showing their versatility. Interestingly, scandium triflate is also an active catalyst for these amide exchange reactions, further highlighting its broad catalytic power.
Scandium triflate pops up again.
It's a very useful Lewis acid. Finally, nitriles, which are at the same oxidation level as carboxylic acids, can be precursors to primary amides. Partial hydrolysis with strong acid is one way, but a milder and fascinating procedure involves reacting the nitrile with an alkaline solution of hydrogen peroxide.
Hydrogen peroxide, how does that work?
The highly nucleophilic hydroperoxide anion adds to the nitrile. The resulting peroxycarboxymidic adduct then undergoes further decomposition, converting hydrogen peroxide to oxygen and water to give the anide. It's a very clean and efficient method for this specific transformation.
This section truly demonstrates the incredible array of tools available to chemists for these fundamental conversions, from classic acyl chloride reactions to powerful coupling agents, and even that peroxide-accelerated nitrile hydrolysis. It's a testament to how chemists have developed highly specialized methods to tackle the intricacies of complex molecule synthesis. The level of control they've achieved is truly remarkable.
It really is. The toolkit is vast and constantly expanding.
Okay, this next section feels really crucial. This is where organic synthesis truly starts to feel like a strategic game of chess. Our sources consistently highlight the critical role of protective groups in multi-step synthesis. What exactly are these molecular disguises, and why are they so essential for building complex molecules effectively?
Think of protective groups as exactly that, molecular disguises or temporary shields. In a complex synthesis, you might have a functional group like an alcohol, an amine, or a carbonyl that would react undesirably with reagents meant for another part of the molecule.
Right, like an alcohol reacting with a Grignard reagent.
Exactly. The acidic proton of the alcohol would react with the Grignard reagent, destroying it.
Yeah.
So a protective group masks that reactivity, preventing this unwanted interference. Then, at a later appropriate stage, it's removed without affecting other parts of the molecule. It's fundamentally about designing compatibility between different reactive sites. The aha here is that you're not just performing reactions, you're strategically preventing unwanted reactions,
Yeah.
which is just as critical, if not more so, in complex synthesis.
So it's about controlling reactivity across the whole molecule.
Precisely. There are three key considerations in choosing an appropriate protective group. First, what exactly needs protecting? Is it an alcohol, an amine, a carbonyl? Second, what are the reaction conditions that the protective group must survive in subsequent steps? And third, what conditions can be tolerated for its removal later on, ideally without disturbing other sensitive groups?
So you need it to be stable when you want it stable and easy to remove when you want it gone.
Exactly. There's no universal group. Each has its own set of compatibilities and selectivities, forming a rich palette of mutually complementary options. While each protection-deprotection step adds steps to the synthesis, making it desirable to minimize them, the methods are usually highly efficient and proceed in excellent yields, making them indispensable in complex molecular construction.
Okay, let's dive into specifics. Hydroxy-protecting groups first.
Yes, let's start with hydroxy-protecting groups. One of the most common requirements is to mask a hydroxy group as a derivative lacking its acidic proton. This is crucial for reactions involving Grignard or other strongly basic organometallic reagents, where the acidic proton would otherwise destroy the reagent. Also, protecting a hydroxy group can improve the solubility of alcohols in nonpolar solvents, aiding purification or reaction efficiency.
Makes sense. What are common types?
Acetyls are commonly used here. The tetrahydropyranol, THP ether, is a classic.
THP ether.
It's introduced by acid-catalyzed addition of the alcohol to dihydropyran. THP groups are remarkably stable to basic and nucleophilic reagents, hydride reductions, and organometallic reactions. They also protect the hydroxyl group against oxidation. They're readily removed by dilute aqueous acid, or even by Lewis acids like lithium chloride, palladium chloride, or copper chloride, which likely promote hydrolysis by generating protons.
But the research highlights a potential disadvantage with THP. A new stereogenic center is formed. How is that problem addressed when stereochemistry is absolutely critical?
Exactly. This is a significant point if you're dealing with chiral alcohols, as it can lead to a mixture of diastereomers, complicating purification. To avoid this, chemists often use methyl-2-propenyl ether, MOP, in place of dihydropyran. This reagent doesn't introduce a new chiral center. Plus, its acetyl is hydrolyzed under somewhat milder conditions than THP ethers. Similarly, ethyl vinyl ether, EE, is also used, though like THP, it introduces a new stereogenic center.
Okay, so MOP avoids the extra chiral center. What about MOM and MEM?
Right, methoxymethyl, M, and 2-methoxymethyl MEM groups are formaldehyde acetyls. They're usually introduced by reacting an alcohol, the deprotonated alcohol, with methoxymethyl chloride or methoxyethoxymethyl chloride. MOM and MEM groups can be cleaved by pyridinium tosylate in moist organic solvents. But a key advantage of the MEM group is its removal under non-aqueous conditions using reagents like zinc bromide, magnesium bromide, titanium tetrachloride, or TMSI.
Non-aqueous removal. Why is that useful?
It allows for incredibly selective deprotection. MEM is cleaved preferentially over MEM or THP under these specific non-aqueous conditions, but conversely, is more stable to aqueous acid than THP. This crucial difference enables elegant orthogonal protection strategies.
Orthogonal, meaning you can remove one without touching others.
Exactly. You can choose the right key, the right deprotection condition, to unlock only the part of the molecule you need to react, leaving other protected groups intact. It's very powerful. The methylthiomethyl, MTM group, is another related acetyl. It can be introduced by alkylation or from dimethyl sulfoxydeacetic anhydride. The MTM group is removed selectively under non-acidic conditions with silver or mercury salts, or by reacting with methyl iodide followed by hydrolysis. The THP and MON groups are stable under these conditions, again offering selectivity.
Okay. What about groups removed by reduction?
Yes, for protected groups specifically designed for reductive cleavage, there's the 2,N,2,2-trichloroethoxymethyl group. This group can be cleaved by reducing agents like zinc, samarium diodide, or sodium amalgam via a beta elimination mechanism, forming a formaldehyde hemiacetal that easily decomposes. And the 2-trimethylsylethoxymethyl, SEM group, offers fluoride-mediated deprotection, example with TBAF, also via a beta elimination mechanism. Here, nucleophilic attack on silicon triggers the cleavage. Interestingly, magnesium bromide can cleave some groups while leaving more hindered silly ethers intact, showing yet another layer of selectivity.
Lots of options there. What about simple ethers as protecting groups?
Moving to ethers as protective groups, simple alkyl ethers generally aren't very useful because their cleavage requires very strong reagents, as we discussed earlier. But the T-butyl group is a notable exception. It's cleavable under moderately acidic conditions, like trifluoroacetic acid or acetic anhydride iron trichloride, due to the remarkable stability of the T-butylation formed during cleavage. It's typically introduced by reacting the alcohol with isobutylene in the presence of an acid catalyst.
Okay, T-butyl is acid-lagal. What about trityl?
The triphenylmethyl, trityl TR group, is removed under even milder conditions than the T-butyl group. It's especially important in carbohydrate chemistry due to its bulk, which usually restricts its attachment to primary hydroxyl groups. Hot aqueous acetic acid often suffices for removal. The ease of removal can be further enhanced by electron-rich substituents on the phenyl rings. This leads to the widely used p-methoxy, PMTR, and p-po-dimethoxy, DMTR derivatives, which can even be removed oxidatively with ceric ammonium nitrate, CAN. The DMTR group is particularly vital in nucleotide synthesis for protecting primary hydroxyl groups due to its selective removal capabilities.
And benzyl groups. They seem common, too.
The benzyl group is invaluable if acid-sensitive groups are present elsewhere in the molecule.
Because it's removed differently.
Exactly. It's typically cleaved by catalytic hydrogenolysis, using hydrogen gas over palladium or platinum catalysts, or by electron transfer reduction, using sodium in liquid ammonia or aromatic radical anions. Transfer hydrogenolysis, using hydrogen donors like formic acid or cyclohexene with a palladium or platinum catalyst, is also common and often more convenient. Non-reductive methods also exist, like using S-butylentensium followed by oxidation. Benzyl groups with methoxy substituents like 4-methoxybenzyl, PMB, or 3.5-dimethoxybenzyl, DMB, can be removed oxidatively with dichlorodecyanoquinone, DDQ.
DDQ, okay.
This relies on the stability of the resulting benzylication. This offers a superb selective deprotection, leaving most other common protecting groups untouched.
And allyl ethers.
Allyl ethers can be removed by isomerization to propanol ethers using bases like potassium T-butoxide or catalysts like RHPPH33Cl, followed by acidic hydrolysis of the resulting enol ether. Wacker oxidation conditions, or debal with catalytic nickel chloride, are also mild cleavage methods, further expanding the arsenal for this group.
These seem to be some of the most versatile protecting groups, according to the research. What makes silly ethers so powerful and ubiquitous in modern organic synthesis? They seem to be everywhere.
They're incredibly versatile, primarily due to their ease of introduction, tunable stability, and mild removal conditions. The trimethylsilly, TMS ether, is very easy to introduce by reacting an alcohol with trimethylsil chloride in the presence of an am. It's also very easy to remove by hydrolysis or exposure to fluoride ions.
But maybe not very stable.
Right, it's quite labile.
Yeah.
But the real strength comes with the T-butyldimethyl. Either
TBDMS or TBS, right?
Exactly, same thing. Its increased steric bulk makes it much more stable to things like hydride reduction and chromium oxidation compared to TMS. While its hydrolysis is slow, it's easily removed by anhydrous tetrabutylammonium fluoride, TBAF, aqueous hydrofluoric acid, or even bromine and methanol.
So TBDMS offers more stability. What if you need even more?
For even greater stability and steric hindrance, chemists use triopropylsilly, TPS, triphenylsilly, TPS, or T-butyl diphenylsil, TBDPS groups. Their hydrolytic stability generally follows the order TMS, TOBDMS, TBDPS.
So you can pick the stability level you need.
Precisely. This graded stability, along with varying sensitivities to fluoride ions, allows for incredibly complex and precise selective deprotections within a single highly functionalized molecule. This is another prime example of orthogonality, where careful choice of the silly group allows you to remove one while leaving others on the molecule completely untouched.
Very strategic. What about esters as protecting groups?
Esterification is another option for hydroxy protection, especially useful during oxidations because esters are generally stable to oxidizing agents in acid. Acetates, benzoates, and pallalates from pavloyl chloride are common choices. They're prepared from anhydrides or acyl chlorides, often with DMA catalysis for speed and selectivity, particularly for hindered alcohols. N-acetylimidazoles also allow acylation without added base.
And removal, usually base.
Yes, base-catalyzed hydrolysis, saponification, is the usual way to remove esters. But if that's not feasible, perhaps due to other base-sensitive groups, special groups like 2-monotidorochloro-2-trichloroethyl carbonate esters can be reductively removed with zinc, which proceeds via a beta elimination. Allyl carbonate esters are also useful. They are deprotected with various palladium-based catalysts that activate the allylic bond for nucleophilic substitution, leading to release of the alcohol, carbon dioxide, and reduced allyl group.
Palladium chemistry again. And what about protecting diols?
Diols, 142 and 143 diols, have a special trick. They can form cyclic acetyls with aldehydes and ketones. Like the common isopropyridine derivatives, often called acetonides, formed from acetone or 2-glycyl dimethoxypropane.
Acetonides, right. Common in sugar chemistry.
Exactly. They are resistant to basic and nucleophilic reagents, but are readily removed by aqueous acid. This method is particularly prevalent and important in carbohydrate chemistry due to the many hydroxyl groups and their precise relative orientations, which allow for very selective protection of certain diol pairs. They can also form cyclic carbonate esters by reaction with reagents like N,N-carbonyl dimidazole.
Okay, that covers alcohols and diols. What about amines? They need protection too.
Yes, onto amino-protecting groups. Amino groups are highly nucleophilic, easily oxidized, and their protons are acidic, meaning they react with strong organometallic reagents. Therefore, protection is often essential to prevent these unwanted reactions.
What are the main types for a menamine?
Carbamatides are extremely useful here because they can be cleaved in various ways, offering orthogonality. The carbobenzyloxy, CBZ group, sometimes called Z, is introduced with benzyl chloroformate. It's removed by catalytic hydrogenolysis, cleaving the benzyl CO bond, causing spontaneous decarboxylation, or by transfer hydrogenolysis. Lewis acids like boron trifluoride with a nucleophile can also cleave it.
So it's stable to base, but removed by reduction or Lewis acids?
Correct. Then there's the T-bucoxycarbonyl, T-bake group, or Bach group. This is another cornerstone, especially in peptide synthesis. It's removed by acid, like trifluoroacetic acid or butylamine sulfonic acid. It's introduced with reagents like T-butoxypyrocarbonate, often called BOC anhydride.
So Bach is acid label, KBZ is removed by hydrogenation. Orthogonal.
Exactly. Orthogonal removal conditions are key. The 2,2,2 trichlorothoxycarbonyl TROC group can be reductively cleaved by zinc. Allyl carbamates, ALA group, are also useful, deprotected with various palladium-based catalysts that activate the allylic bond for nucleophilic substitution, involving an oxidative addition to palladium followed by a reductive elimination.
Palladium again, like the allyl carbonates.
Yes, similar chemistry. And substituents like allyl groups attached directly to the nitrogen can be removed by isomerization and hydrolysis, similar to allyl ethers. Interestingly, 2-nitrobenzyl carbamates are special because they can be removed by photolysis using light.
Photochemical deprotection, cool.
Yeah, the photoexcited nitro group abstracts a hydrogen, leading to a deprotection cascade. N-benzyl groups on tertiary amines can even be removed by reaction with chloroformates, providing amines to delegate tertiary amines selectively. For amides and amides as protecting groups, simple amides are generally only effective if vigorous hydrolysis, strong acid or base, is acceptable for removal later on. However, phthalamides are a common protecting group for primary amines, as we saw in the Gabriel synthesis. They're cleanly removed by hydrazine, or, more mildly, by sodium borohydride in aqueous ethanol. Trifluoroacetamides are easily hydrolyzed due to the strong electron-withdrawing trifluoromethyl group, allowing their use as a protecting group under mild hydrolytic conditions. Benzamides and trichloroacetamides can be deacylated by careful partial reduction to the carbonylamine stage, followed by hydrolysis. The 4-pentanoid group is fascinating because it's removed by iodine through an iodocyclization and hydrolysis of the resulting aminolactone.
Wow, iodine triggers it.
Yes, very specific. Sulfonamides are generally difficult to hydrolyze, but a clever photoactivated reductive method using sodium borohydride and dimethoxybenzene has been developed. Additionally, cyclic bisilly derivatives, like disilazolidines for anilines, offer protection stable even to organometallic reagents. And 4-methoxy, or 2.4-dimethoxyphenyl groups on amide nitrogens, can be removed oxidatively with CAN or with anhydrous trifluoroacetic acid.
Okay, a whole suite of options for amines too. What about protecting carbonyls, aldehydes and ketones?
Right, finally, carbonyl protecting groups. Aldehydes and ketones are highly susceptible to nucleophilic addition and reduction, so they often need masking. Converting them to acetyls or ketols for ketones is a very general and widely used protection method.
Like the diol protection, but now protecting the carbonyl itself.
Exactly. Ethylene glycol forms cyclic dioxylines by heating with an acid catalyst and azeotropic water removal. Scandium triflate is also an effective catalyst for this. Dimethyl or diethyl acetyls can be formed by acid-catalyzed exchange with orthoesters or 2.2-dimethoxypropane. A very mild method uses trimethylylsilane ethers with trimethylsilyl triflate as a catalyst.
And removal. Acid again.
Yes, for deep protection, acid-catalyzed hydrolysis is standard, but Lewis acids like lithium tetrafluoroborate or bismuth triflate also work. If non-hydrolytic deep protection is needed, acetyls from beta-haloalcohols like 2-corn-2-trichloroethanol can be used, then removed by reduction with zinc via beta elimination.
Okay. Any other carbonyl protection?
1,3-oxyethylene derivatives from mercaptoethanol are also useful, especially when non-acidic deep protection is required. They can be removed with Raney nickel or mild halogenating agents like N-bromosuccinimide, NBS, which oxidize the sulfur and trigger hydrolytic cleavage. And dithioketals, cyclic dithiolanes and dithions, are very robust carbonyl protecting groups. They're formed by Lewis acid-catalyzed reactions of dithiols like ethanodithiol. Their regeneration involves reagents that oxidize or activate the sulfur, facilitating hydrolysis, such as nitrous acid or cupric salts.
So sulfur gives different removal options. Lastly, carboxylic acids. Can they be protected?
When it comes to carboxylic acid protecting groups, protecting the OH of a carboxyl group is relatively easy. Just make an ester, as we discussed. Alkaline hydrolysis is the usual way for regenerating the acid. T-butyl esters, which are readily cleaved by acid, can be used if alkaline conditions must be avoided, and 2,2,2-trichloroethyl esters can be reductively cleaved with zinc. The more difficult problem is protecting the carbonyl of the carboxylic acid itself, as it is relatively unreactive compared to aldehydes or ketones.
Right, it's less electrophilic.
Exactly. This can be accomplished by converting it to an oxazolene derivative, like the 4,4-dimethyl derivative. This protects the acid from Grignard or hydride reagents. The acid group can then be regenerated by acidic hydrolysis or converted to an ester. More complex orthoesters, like 4-methyl-2-647 trioxybicyclo 2.2.2.2 octane, are also useful protecting groups. They are formed by exchange or rearrangement. Lactones can be protected as dithiolane derivatives using trimethylaluminum and ethanodithiol. Acyclic esters can yield ketone dithioacetals with this reagent. Overall, though, carboxylic acid carbonyl protection methods are generally less convenient than for alcohols or aldehydes.
So what's the workaround?
A common strategic trick is to carry potential carboxylic acids through a synthesis as protected primary alcohols or aldehydes, and then oxidize them to the acid late in the process. This leverages the wider variety of highly effective alcohol and aldehyde protecting groups indirectly for carboxylic acid protection. It showcases the creative problem solving involved.
That's clever. Use a precursor. This entire section on protection and deprotection truly shows the elegance and foresight required in designing complex syntheses. It's not just about what reactions you can do, but what reactions you strategically prevent from happening and how you set up your molecule to achieve the desired outcome with absolute precision. It's a masterclass in molecular strategy and problem solving.
It really is. It's thinking like a chess player, but with molecules.
What a fascinating journey through the world of functional group interconversion and protection. From activating those stubborn alcohols and precisely swapping out atoms, to building complex carbon frameworks with SN2 reactions, and even temporarily disguising sensitive parts of a molecule with protective groups. We've seen the sheer ingenuity involved in modern organic synthesis.
Indeed. Understanding these substitution reactions, their precise mechanisms, like SN2, SN1, additional elimination, and the strategic use of protective groups, is absolutely fundamental to building complex molecules efficiently and selectively. It highlights how chemists leverage subtle differences in reactivity and carefully selected conditions to achieve astonishingly precise molecular transformations, often on a very small scale initially, which then can hopefully be scaled up for industrial applications. The ability to manipulate molecules at this level is what underpins so much of modern chemistry and its impact on our lives.
So whether you're trying to synthesize a new drug, understand a biological process, or just gain a deeper appreciation for the intricate molecular world around us, remember the power of these interconversions and the art of molecular protection. They're the silent heroes of countless chemical breakthroughs, enabling the creation of materials and medicines that truly shape our lives.
Couldn't have said it better myself. They are truly foundational concepts.
We hope this deep dive into functional group chemistry has given you plenty of aha moments and sparked your curiosity even further about the incredible world of organic synthesis.
Hopefully it demystified some of those complex-looking reactions.
Thank you for being part of our deep dive family. Until next time, keep exploring, keep learning, and keep being brilliantly informed.